Thank you, Paolo. Thank you, everybody. And thank you for having me here in Singapore. I have family here, so I come regularly, but I do have problems with your weather. So I like the air conditioning. My talk is very different in that I'm working a lot with farmers now to try and do two things. One is to help them see that there is a future in farming in Australia in the light of climate change. And the other is we have an aging population of farmers. So what we're trying to do is to give them resilience and give them and help them with their just with their mental health to show that there is an actual future. My talk basically this year is I'm going to read it actually because of a time factor. With increasing medium and high density urbanization around the world and the limiting of natural resources, upvaluing waste streams so that they can be valued as resource streams is becoming increasingly important. The impact of changing climate on weather patterns puts increasing pressure on crop production because of increased pests and diseases encouraged by the warmer, wetter weather in agricultural zones around the world. So what we've got is a lot of the waste, and it's organic waste that is going into landfill. And these are disgraceful, shameful photographs of landfills in Australia. And this is what my work is trying to alleviate to some extent. At the same time, the urban waste is increasingly going to landfill because there's no apparent will to recycle to the extent that's needed to use all of the waste products generated by the community. Here it is organic waste that is being discussed. So I'm not talking about other hard waste, other rubbish. I'm talking about organic waste that has a potential new use. We call it FOGO in Australia for short, food organics, green organics. And it can be recycled by thermal aerobic composting, digester composting in anaerobic systems, and windrowing where there's a lot of space. All of these methods produce an organic product that will enhance soil health, stimulate soil biota, improve nutrient content of foods grown in these materials, and lead to carbon capture, reduce greenhouse gas emissions, and improved plant, animal, and human health. We have these bins that we ask our urban community to use and to separate. But what we're finding is that the separation is really not as good as it could be. So it creates problems. And this is another disincentive that we have to deal with. 2 years ago, I received a significant grant from Sustainability Victoria, which is one of our government departments, which has major programs addressing recycling and reducing waste, reducing emissions, supporting Victoria's transition to a circular economy. What is happening here is this is our own farm, and these huge trucks move this organic waste around from the urban areas out into areas where they can be composted, either as right through it in a windrow situation, or as I say, as thermal aerobic, or even through the digesters. And so as part of a project, AgPath, which is my company, we're a leading researcher. We applied for and we were successful in receiving a major grant to investigate raw materials such as FOGO and feedlot manures. Feedlot manures is another big problem that we have in Australia, is how to utilize that and how they can be incorporated into the resource stream for farmers as a fit for purpose product. A lot of these things are put out just as raw materials, but they're not necessarily fit for purpose when we consider fungal bacterial ratios, when we consider carbon nitrogen ratios in our soils. So the raw materials and the finished compost from a commercial producer was delivered to our place, and these are some of the basis of the research work that we went on to do. Unfortunately, all the council collection agencies in Victoria, both metropolitan and country, are finding that people are not being serious about the correct use of their various bins. Here we're showing the contamination that was coming from the FOGO, coming from the food organic, green organic bins. Over 100 hours by my staff, and that was 4 of them, were taken in cleaning up over 1,000 kilograms of rubbish from 40 cubic meters of FOGO. This is a huge amount of contamination. This makes the FOGO unusable by farmers and is a great disincentive for the uptake of this nutritious resource. Receiving stations are having to install expensive sorting and screening stations to pre-sort the rubbish from the FOGO before it can be mulched. Now, this means hundreds of thousands of dollars go into screening, putting in screening equipment that screens out plastic, glass, metal, all things that shouldn't have been in the FOGO bins in the first place. So it adds to the cost of the mulch that then goes out from the sorting companies out to the farmer, which means an increased cost to the farmer for using this really valuable resource. What we did during this research was we took FOGO and the feedlot manure, because these were the 2 raw material resources that Victoria sees as not at the moment fit for purpose. And we were blending them at different rates and allowing them to mature at different rates. So we looked at blends of 25 to 75%, 50-50, 75% to 20, feedlot manure with finished compost and feedlot manure with FOGO were used as treatments on replicated trials. So we did fundamental science as well as this general science, using 2 different soils, which were pasture soils for stock. We used 2 different soils that were vegetable growing soils, because I live in the middle of a large vegetable growing area. And we used baby spinach and snow peas, which are very highly sought fresh vegetables on the Victorian market. And we grew them across the winter and summer period. These were the trial plots, the replicated trial plots. We had 6 treatments. We had 3 replications at 2 meters by 10 meter plots. And we carried these out. They're still being used. So we're into our 3rd year now. Because of a certain sort of difficulties in trying to work with the farmers with their vegetables, given that some of their crops are only 28 days and 52 days, we found it difficult in trying to have them work with us for our timetable versus their timetable. So Sustainability Victoria said, please take the plots and make them above ground plots. Don't put any bottoms in them. Try to get it as natural as possible and do the vegetable part of the research in these replicated plots here. So we had a random block design for our 2 soils and our 5 or 6 treatments. And so this is what they're showing here. And then this is how we were growing a known number of seeds in a layout of 3 rows in our various plots. And so it was as close as we could get to a natural system. The trial data included 35 parameters of soil temperature, diversity of plant species in the pasture, soil biology, nutrient in the plants and the soil. And this data it's with a statistician at the moment for analysis. Initially, we were looking at how to encourage farmers to take a regenerative biological approach to farming and to move away from synthetic chemicals, pesticides, herbicides, and fungicides. The bottom line is important. We compared the cost of raw materials delivered, the cost of synthetic chemicals, figures directly from a chemical supplier, and the cost of making compost and compost tea. Organics came out ahead where there was reduced added costs of fungicides, herbicides, pesticides, because the organic regenerative crops and pastures were healthier and with less pests and diseases, particularly with mildews and ruts, and with fewer weedy species in the pasture and vegetables. We've been on our farm for 55 years. We have not put a synthetic chemical on that farm in 55 years. We use fish and kelp, molasses, rock dust. We use compost and compost tea. And our farm is used by the government as a farm or a farm that they bring people to show what can be done with alternative agriculture. We run Angus beef. The herd is raised and lowered in number depending on the availability of grass. We don't cut hay. We don't need to cut hay. We have pretty cold winters. We can get on average maybe 35 frosts through the winter, but our stock do not need supplementary feeding because they have plenty of grass even through the winter. And we put this down to the biological activity of our soil. When moving from conventional farming inputs to biological inputs, it is the soil that is being prepared so that the soil biota can generate the plant available nutrients for the crop. Remember, it's the microbiology that drives the plant available chemistry in the soil, not the other way around. No microbes, therefore no long-term productivity. It's the carbon-nitrogen ratio of the organic inputs that will improve soil health and productivity, allowing for more decomposition or more rapid decomposition of the organic matter in the soil and more plant available nutrients. We were looking at the best nitrogen mineralization and the blend that contained the FOGO, the food organic, green organic manure, in any proportion that appeared to enhance mineralization. Our data is very preliminary as yet. So we haven't determined which blend may be the best, but at the moment it looks as though 50-50 of the feedlot manure, aged feedlot manure with the food organic, fresh food organic, green organic from the urban waste stream is the one that may be giving us the best ratio of carbon to nitrogen and also the best fungal to bacterial ratios in the soil. These products will reduce methane emissions from animals on better nutrient pasture resulting from organic inputs with increased fertility. Result in reduction and elimination in the use of synthetic nitrogen fertilizers where there is a poor nitrogen use efficiency and high wastages through the gaseous ammonia losses and pollution. FOGO-M is an inherently resource conservative process that retains carbon and key plant and microelements when applied back into the soil. Using Victorian government statistics for 2022, local government annual waste, this is our urban waste collection, amounted to nearly 650,000 tonnes of organic matter that could be recycled, but isn't. Cattle manure in 2022 was estimated, this is from the feedlots, was estimated around 2 million tonnes. If we convert that then to greenhouse gas emissions, for example, methane, nitrous oxide, carbon dioxide, dry FOGO is equal to about 217 kilograms of carbon dioxide equivalent per tonne. Dry compost in landfill, and that's mostly anaerobic, is a bit over 1,000 kilograms of carbon dioxide per tonne. So if we divert FOGO from landfill, we can assume that carbon dioxide equivalent tonnage reduction, this is using our 50-50 blend, if that's the one that works out correctly. Feedlot manure on Queensland, on Victoria figures is over 6 million kilograms or 6,000 tonnes of carbon dioxide reduction annually. These figures are based on a really good paper by Perez et al. 2023. So if we just take our feedlot manure and we take our FOGO and we utilize it as a mulch or as a compost, even through digestion or through thermal aerobic compost, we can pull out so much carbon dioxide, just city by city, if we had a will to do it. And these are the figures up there. But that paper by Perez and al. Is worth looking at. This is our property. These slides show the windrows and the ring compost blends that we use for the trials on the 50/50 FOGO feedlot manure. Appears to be giving us the best fit for purpose product. So what we've done by introducing organic matter back into the soil, minimizing ploughing, removing synthetic chemicals, we've begun to restore soil food web. We are allowing the microbes of the soil to provide the nutrients for the plants. We are allowing them to improve the plant resilience in the face of pests and diseases. Healthy plants and animals rarely ever get sick. High Brix in plants has a direct effect on many pest insects because their gut and digestive structure does not allow the intake of nutrients that are high in sugars. If you have a look here, if we can, everything is predicated on photosynthesis. All our plants grow, they have exudates, and that the plant roots then have sloughing off in that rhizosphere zone. So what we need when we've got a fully functioning soil food web, we've got the bacteria, particularly, and the fungi, and the little shredders feeding on that organic matter, breaking it down to the elements that we require for plant availability. But the bacteria and fungi aren't terribly good sharers of this nutrient. So we require the next trophic level, which is the protozoa and the nematodes and the earthworms and ants, etc., to eat this highly concentrated carbon to nitrogen ratio material. And in the process of digesting this, they're releasing plant available nitrogen, one of the many sources of natural nitrogen that we can have in the field. And so if you have a look at all those arrows, when you put high amounts of synthetic chemistry onto the soil, those arrows largely disappear. Many of the microbes that form part of the soil food web are lost. And so our soil rapidly becomes back or goes back to dirt because we've lost the organic capacity, because at the same time as all of this conversion or lack of conversion happening, we're also losing organic matter from the soil. Because the systems that use high synthetic inputs usually plow. They don't look at pasture cropping. They don't look at adding the organic matter back in again, which will sustain the soil food web. And therefore we end up with a totally synthetic system that in effect is not sustainable. We need all of these organisms in a healthy soil. The protozoa, the nematodes, the earthworms. On our soil, on our farm, which I say hasn't had a synthetic chemical on it in 55 years, when we put a spade into the ground, depending on the time of the year, we can get between 37 and 55 worms per spade of soil in our soil. And that is very, very healthy soil. You can see the castings. It smells sweet. It's good soil. We're allowing the soil and its biota to sequester carbon, hold water and nutrients, and provide a healthier and more nutritious plants. We're looking at the minimization of interference in the growing process and managing the natural resources of nitrogen and phosphorus, for example. There are so many sources of natural nitrogen: the atmosphere, nitrogen fixing bacteria, the soil food web functions, composting of organic matter. And this particular slide shows that the plant available nutrients that could be available if we had a 100% cover on our soil 100% of the time. So we're sequestering carbon. We have then a fungal dominated soil from which less carbon is emitted than with a bacterial dominated soil. We have a root system that goes further into the ground and therefore builds up the mycorrhizal fungal biomass that allows us to sequester carbon and allows us to hold water. And particularly in a country like Australia, where we're having indeterminate rainfall, we're going to need to look at getting together all the water that we can. By minimizing interference, what we can do is look at how we can use more of the natural nitrogen, because always the farmers or the agronomists in Australia say, oh, you've got to add nitrogen because you're taking off more than you're producing. Well, in a synthetic soil you are, but in a natural biological soil, you actually may not be. And what I say to my growers is go to the peak bodies. If you're a dairy producer, if you're a beef producer, if you're a grape producer, find out how much NPK is taking off per litre, per kilogram, per tonne of nitrogen. And what you have to do is make sure you produce and have left more nitrogen than you're taking off. And you can do that in a biological system. Organic material. Here on this particular here one, when you put organic material into the soil, it's not plant available. All of the manures, the solids, the plant residue is not plant available until the microbiology breaks it down into the inorganic forms. And once you do that, you've got your ammonium and you've got your nitrate. And what we find in Australia again is we have very, very high nitrate or nitrate broken down to nitrite in the soils because of excess input of urea. And if you have a perennial system, the perennial plants require their nitrogen in the ammonium form more so than they do than in the nitrate form. Weedy species, for example, the first colonizers, they require a higher nitrate form. So what we have to do is look at what are we growing? What are we wanting to do? We're wanting to sequester carbon. We need a 100% cover 100% of the time. We need it for a perennial system. We need more ammonia nitrogen than we need nitrate nitrogen. So what we have is this mineralization that's carried on by the microbiology. We have the mineralizers, the demineralizers. There's a whole group of them that are there specifically just to do this. And so they mineralize the organic nitrogen into an inorganic form, and then it's plant available. But at the same time, they have to live themselves. So they have to draw on some of this inorganic nitrogen just for their own reproduction. And this is the immobilization phase of this. But if we have a good organic system where we have mineralization greater than immobilization, but we have an increasing population of our microbiology, then we have a good healthy soil. We've got net mineralization of nitrogen that's plant available. And so we can have an organic system, a biological system, a biodynamic system, a regenerative system, call it what you want. We are actually building our soil as our major resource, not what we're producing. We're making our soil our major resource, and we can do that. In the course, I was getting some material ready for my students, and I came across this paper by David Thomas, which horrified me. What he did is he looked at production post-Second World War, after the munitions use of ammonium nitrate during the war. The people in charge decided we can't have all of these factories go out of business. We have to do something with it. So let's dump it on the poor farmers, cheap fertilizer. However, that has caused an acidification of our soils. It has caused a decline in the quality of the production that's coming off our agricultural lands. And in some places of the world, the agricultural land now, the products that are coming off that agricultural land are now so toxic they can't be eaten by either plants, by either people, or by animals. And so we've got to reverse this. But when I look at this, I think, oh, wow, this is what's coming out of our supermarkets. It's not what's coming out of my garden, but it's what's coming out of our supermarkets. And when you look at that decline in quality of food nutrients, then this is a wake-up call. This is why maybe there's an increase of illnesses in the world, because our food may be quantitatively there, but qualitatively and nutrient rich it's not. And so we have to change the system. We have to go to a system that our great-great-grandfathers and grandmothers knew all about. We have to go to caring for country. We have to care for the soil. If we care for the soil, then we can grow anything above the ground, and we can grow it in a much more healthy state. So I say to everybody that works with me and to all of my students and to the farmers I work with, we care for country first. We produce something above the ground second. If you have a look at industrial farming versus biological regenerative, I mean, there's so many names, organic, biodynamic, it doesn't matter. It all means it's industrial farming versus caring for country. And so when you open up land through ploughing, you lose all of that fungal biomass, that mycorrhizal biomass that is so important in holding moisture in the soil, in providing phosphorus, etc., for our plants. And so you have a loss of all of the soil capacity to be able to produce healthy foods. We have an increase in pests and diseases because sick plants get sick the same way as sick humans get sick. And the synthetic input is so great, it's not sustainable. But if you have a look at the other side, if we care for country, if we looking at our soil first, getting our soil microbiology working so that it can produce all of the plant available nutrients, or most of the plant available nutrients that our plants need, what we find, we don't have to produce as much food if we produce better food. And I have farmers down in Gippsland, down in Victoria, where I live, where they've actually reduced their herds significantly, 25–30%, fewer milking cows. They've increased their productivity significantly, 30 and 40 and 50%, where they've gone from an industrial agricultural system to a biological system. It's taken them a couple of years, but they find now that they can see a future for their farm. They find now that they have some spare time because they're not chasing a dollar the whole time. Their milk production is going up by milking less cows, and that's just cows. With vegetables, it's the same way, and it's the same thing that's happening in Australia. We're starting to encourage farmers to look at not only care for country first, look at a crop second, but have a look at some of the carbon trading that's going on. It's becoming a new thing, probably in other countries as well. And so the farmers are starting to see that there is a future, because we have a lot of loss of life among farmers out of just despair. And that's not fair, because the rest of us, oh, well, I'm a farmer, so I'll include myself there. People who are living in the city can only live in the city because farmers do what they do. More respect, pay value for your food. And if we do it biologically, then we've got a future. And as Professor said, it's not one, whatever that saying is, one fits all. There are nuances that we have to encourage. But if we encourage their direction towards minimization of input, which he's talking about, and maximization of food and production health, then we have got a future. Because it's absolutely true. The nation that destroys its soil destroys itself. Thank you.